Now we'll start group theory, and obviously it is an important topic in abstract algebra. And first we'll do some theoretical explanation, and then we'll continue some problem related to each concept of the theory. Now first we'll start the definition of group. Definition of a group. So for that we need one non-empty set and one binary operation. So let G be a non-empty set, and not be binary operation, be any binary operation on G. Then the algebraic structure G naught, then G naught is called group, if it satisfies following condition. If it satisfies following condition. So as we said, the condition 1, as we said, not the binary operation of G, so obviously closure property holds. So that means A not B belongs to G for all AB belongs to G. So this is basically for the binary operation. So if not is a binary operation on G, then A not B belongs to G for all AB belongs to G. And this property is also called closure property. The second important property is the associativity property, that will also hold. That means A not B not C, that will be A not B not C for all ABC belongs to G. So this is called the associative property. Third is talking about the existence of identity. So that means there exists an element E belongs to G such that E not A equals to A not E equals to A for all A belongs to G. And this property is called existence of identity. I said there exists the existence of identity. Next, the fourth property to be a group. So this is called the existence of inverse. That means for all A belongs to G, there exists an element B belongs to G such that A not B equals to identity. A not B equals to identity equals to B not A. And this is called existence of inverse. Okay. So the first property is the closure, second is associative, third is existence of identity, and fourth one is the existence of inverse. If all the properties holds, then we conclude G naught is a group. So we have taken a non-empty set G. G is non-empty. Along with the operation not, that algebraic structure forms a group if it satisfies the following condition: closure, associative, existence of identity, and existence of inverse. So note, if it satisfies all the property, then we say G with this algebraic structure not is called a group. So now we'll give some example of group, but before that, there is another important note. If the only closure property holds, then the group is called group wide. closure plus associative, it is called semi-group, and closure plus associative plus identity, that comes under the monoid. So only closure that implies groupoid. Closure plus associative property, associative, that implies semi-group. Now closure property plus associative plus existence of identity, that implies monoid. And closure plus associative plus existence of identity plus existence of inverse, that is basically group. Okay, so what we said here, if there is only binary operation and other property not holds, then up to this it is called groupoid, not group. If both the condition closure and associative holds, then it is called semi-group. The first three conditions, that means closure, associative, and existence of identity, that comes under monoid. All these four property holds, this is basically group. Okay, that we must recall. So now we'll start with one important problem. Okay, and before that we will give the example. The example is R with the operation plus, this is our group. What is R? Where R is basically the set of all real numbers. Similarly, the Q plus set of a rational number with respect to the addition, this is also a group. We need to verify all the property holds or not. That means it is closure, associative, the existence of identity and existence of inverse, all the property you will verify, you will check, this is and group. Now come to the problem. So problem number 1 is the set R star So here R star means set of all non-zero real number, R star of all non-zero real numbers forms a group with respect to the operation not defined by A not B, this is equals to mod A multiple B. Justify. Okay. So this question is very, very important. Is it a group or not? How to check? So what is exactly given? We'll come to later, it is group or not, but what is given? R star. R star means R minus 0. So that means set of all non-zero real numbers. This is the first thing. The second thing is the operation not is defined by A not B equals to mod A into B. Now, what we justify? We justify that say just to consider if possible let first we check closure associative property it holds. If possible let E be the identity element, E be the identity element, then what we can say? For all A belongs to R star, A not E, E not A, and that will be A. This is the property of the identity element. So in particular, if we take in particular, if we take E equals to 1, then what will happen? 1 not E equals to E not 1, that will be A. That will be 1. And that implies 1 not E, that means mod 1 E equals to mod A into 1, that will be 1. And from the first case, what we can say? We can say from this case, we can say E equals to 1. And from the other case, that means from the second case, we take last two relation that comes under mod E equals to 1. That means here, therefore E equals to either 1 and minus 1. So this relation holds for minus 1 as well as for 1. Okay. So that means it has two identity, but we know that identity element is always unique. Since identity element in a group is unique. So this is a contradiction. I can write which is a contradiction as identity element in a group is unique. So therefore, set of all non-zero real numbers with this operation not is not a group. Now we come to the next important definition. The definition is called the commutative group. What exactly mean the commutative group? So just to see the terminology, to be a commutative group, first it holds, it is a group, then we have the commutative property here, and it will be the commutative group. So what should be the definition? A group G naught, that means already it has notice closure, associative, identity inverse, all are exist, all are basically holds. And that group is said to be commutative. Commutative group, or sometimes it is called abelian group. Abelian group if the commutative property holds. If A not B equals to B not A for all A B belongs to. So this is a group. That means closure, associative, identity inverse all holds. Plus we need to add the abelian property. Because what is abelian property? Take any two element of the group G and what will hold? A not B equals to B not. So this property is called abelian. If it holds, then the group is called commutative group. So if you have asked an example of a commutative group, example. Okay. So here one good example of a commutative group is, say, Zn plus, this is an example of a commutative group, is an abelian or commutative group. Okay. While what is Zn? Zn is basically the element which are basically the remainder when an integer is divisible by n. So remainder will be 0 or 1 or 2 up to n minus 1, integer modulo n. Okay. And you will check this is an abelian group with respect to addition. Okay. In fact, we will see this is a group of order. Note, you will see later this is a group of order n that contains n element. So that means number of element in Zn. Now we'll do another example along with the problem. The problem is very important. Let G equals to all those complex number Z belongs to C such that mod of Z equals to 1. What is C? Where C is basically set of all complex numbers. So that means it is of the form A plus IB, where AB belongs to real number and I is basically root under minus 1. Show that G is a commutative group. G is a commutative group with respect to usual multiplication on C. Usual multiplication on C. So multiplication is the operation here on complex number. What exactly we mean the multiplication in complex number? With respect to that operation, you have to prove, you have to show G is an abelian group. Now what is our set? Our set is all those complex numbers whose modulus is 1. That means if we draw, this is your real Z and this is your imaginary Z. So the number which the element which lies on the unit circle on the complex plane. So here the radius is 1 unit. In that case, mod Z equals to 1. So 1 0. This point is 0 1 I and minus 1 0 and minus 1. That element we can consider 1. That element we can consider minus. So all the elements on the circle, on the unit circle, is basically elements of G. All the elements on the unit circle, that element, all these elements are basically elements of G. So now what we have to show? We have to show G is, we have to show that this is a commutative group. So where dot is basically the usual multiplication. So for commutative group, first we show closure property, Roman 1. Just you have taken two elements, let A comma B belongs to G. So then obviously mod A will be 1 and mod B will be 1 because G contains all elements whose modulus is 1. Now what we have to show? We have to show AB belongs to G. Okay. Now it is clear. Now it is clear that if we take two complex number, the product of two complex number must be a complex number. So A dot B belongs to C. And if we take modulus of A dot B, that will be mod A into mod B. It is a property of complex number. So that will be 1, 1. It will be 1. So AB belongs to complex number, the multiplication, and A dot B that modulus 1. So AB belongs to G. So what we have said, for all AB belongs to G, that implies AB belongs to G, and hence G is closed under multiplication. Hence G is closed under usual multiplication. Here one note is important. Here A dot B and AB have the same meaning. Dot is basically usual multiplication. Now the closure property holds. Now we come to the associative. So what we will take? We will take three elements A, B, C belongs to G. Now what we have to show? We have to show AB C equals to ABC. Okay, that we have to show. Since ABC belongs to G, so mod A equals to mod B equals to mod C, and all are basically 1. So now, if we take ABC, that modulus, so it will be mod AB, mod C, so that will be mod A, mod B, mod C. This will be 1, 1, 1, so that means 1. Again, if we take ABC, that modulus, it will be A mod BC, A mod B into mod C. So again it will be 1, 1, 1. So that means A dot BC equals to ABC for all ABC belongs to G. So thus ABC equals to ABC for all ABC belongs to G. ABC belongs to G. And that also you can say from hereditary. Since G is associative under multiplication, so obviously G is a subset of C, so associativity automatically holds by the hereditary property. Now we come to the third case, that means the existence of identity. Okay. So here we seen that we have 1 belongs to G. Why 1 belongs to G? Because modulus of 1, this is equals to 1. And 1 dot A equals to A dot 1 equals to A for all A belongs to G. That means 1 is the identity element. The identity element in G. So existence of identity is done. Now inverse. Say let A belongs to G. Then mod A equals to 1. And also we can write 1 by A belongs to G. Why 1 by A belongs to G? Since modulus of 1 by A, that means 1 by mod A, that means 1 by 1, it is 1. So 1 by A belongs to G. Now we see that A dot 1 by A, that will be 1. Also 1 by A multiplication A, that is 1. So that implies 1 by A belongs to G is the inverse of A. So therefore we can say for all A belongs to G, there exists 1 by A, this is belongs to G, such that A dot 1 by A, 1 by A dot A equals to 1. So that means 1 by is the inverse. So existence of inverse is done. So now we conclude. So all the property closure, associative, identity, inverse, all are done. So therefore we can say G with the usual multiplication, is a group. Now we will check property number 5. This is the abelian. Abelian property hold. Let A comma B belongs to G. Then mod A equals to 1 and obviously mod B equals to 1. What we have to show? A dot B equals to B dot A. Okay. So now in the complex number we have for any two complex number A B, A dot B, A multiplication B and B multiplication A holds for all A B belongs to C. That we know. So therefore we can say A dot B equals to B dot A for all A B belongs to G. Why? Because G is a subset of C. So that means here G is not usual multiplication holds the commutative property. So G is an abelian group. G is an abelian group with respect to usual multiplication. Okay, so we proved that this result. Now we come to next important question. Question number 3. Show that the set of all the set of all 2 cross 2 real orthogonal matrix from a group with respect to matrix multiplication. And also show that this group is not commutative. This group is not commutative. Set of all 2 cross 2 real orthogonal matrix is also example of an non-commutative group with respect to matrix multiplication. So the first part, but before that, what exactly mean by the set of orthogonal matrices? Let O2 cross 2 be the set of all 2 cross 2 real orthogonal matrices. Okay, that we consider as G. So G will be all those A, B, C, D 2 cross 2 such that A comma B comma C or D all are real number and A transpose A, this is basically identity of order 2 cross 2. So this is the definition of set of all real orthogonal 2 cross 2 matrices. Okay. Sometimes we can write here A belongs to M to R such that A transpose equals to A transpose A. This is equals to identity. Now we have to show that it is a group but it is not commutative. So first we think about the closure property. So if we take two element here, let A comma B belongs to G. Then we have to show that AB is the multiplication of two orthogonal. The multiplication of two orthogonal matrices is orthogonal. Since AB belongs to G and G contains set of all 2 cross 2 orthogonal matrix, so A transpose equals to A transpose A equals to identity, and B transpose equals to B transpose B, and that will be also identity. Now, since A belongs to M2R, B also 2 cross 2 matrix where N is a real number. If we multiply AB, AB obviously are matrices of order 2 cross 2 and all the entries must be real numbers. Now we calculate AB is orthogonal or not. So what we will do, AB transpose AB. So what exactly means? That will be according to the transpose formula, AB transpose B transpose A transpose AB. With the help of associative law, we can write A transpose A and B. So this is by associative law. Associative law. And this is by XY whole transpose, that will be Y transpose X transpose. Now A transpose A, that is basically identity. So B transpose I B. Why it is given? A transpose A equals to identity. So this is Roman 1 and Roman 2. So by 1, it is given A transpose A equals to identity. And that will be B transpose B. And this will be again identity. Since by 2, what we have, B transpose B is also identity. So that means we have put here AB transpose AB, this is equals to identity. Similarly, you will check AB whole transpose, this is also identity. So that means AB is an orthogonal matrix, so AB belongs to G. Since AB is orthogonal matrix and AB belongs to M2R. So closure property holds. Now we'll check. So therefore, we can conclude the product of 2 orthogonal matrices is orthogonal for all AB belongs to G. Now we check associative property. Now we'll check associative property. You know, for any matrix, the multiplication is associative. So we know ABC equals to ABC for all ABC belongs to M2R. And since our G is subset of M2R, so obviously by hereditary property ABC equals to ABC that holds for all ABC belongs to G. This is by hereditary property. So associativity property holds. So therefore, what we can say, ABC, this will be A multiple BC for all ABC belongs to. Now we come to next property, this is the existence of identity. Existence of identity. How you will prove the existence of identity? You know, for any matrix, if we multiply by identity matrix, that will again the same matrix will appear. So we know we have the I2, it means 1 0 0 1, that matrix belongs to G. Why? Because I2 transpose I2, I2, I2 transpose. This will be again I2 because it is an orthogonal matrix. And also we see that if you take any matrix, multiple identity matrix, and identity matrix multiple, it will be again A. That is hold for all A belongs to G. And that implies I2 is the identity element in G. So existence of identity is holds. Now we come to the existence of inverse. Now we'll move to the last property for group, existence of inverse. So let A belongs to G. Now we need to find out the inverse. Since A belongs to G, then A transpose equals to A transpose A. That will be identity. Now since A transpose equals to identity, so that implies determinant of A, that will be plus minus 1. And that means if we take determinant on both sides, that means the determinant of A is non-zero. And that implies A inverse exists. And we have to check A inverse exists, but we have to check A inverse is orthogonal or not. So therefore A belongs to G implies A inverse exists. Now we'll check A inverse whole transpose A inverse. Okay, so that we can write A transpose inverse A inverse. Since A transpose inverse, that we can write A inverse transpose. The property of the transpose, interchange it. That we can write A transpose whole inverse. And since XY inverse for any two matrix, it will be Y inverse X inverse for all XY belongs to M to R, but inverse of X and Y exists. A transpose means identity inverse, that means again it will be identity. And similarly, in similar way, you will check A inverse whole transpose, again it will be identity. That means A inverse belongs to G. As A inverse is orthogonal, so A inverse belongs. The inverse of each element exists. Okay. So therefore, A inverse belongs to G for all A belongs to G. Okay. That means for all A belongs to G, there exists element A inverse belongs to G such that A inverse equals to identity equals to A inverse A. So thus all the properties holds, closure, associative, existence of identity and existence of inverse. So we can say G is a group with respect to matrix multiplication. Matrix multiplication. Now we'll come to the second part. It is commutative or not. Second part, just we'll check the commutative properties. So let A and B be two elements of G. But in general, what we know, in general, we know matrix multiplication is not commutative. Okay, that means that is AB not equals to BA in general. And from that case, we can choose two orthogonal matrix which is not commutative. So here we can check. You can check by taking two example of orthogonal matrix. So AB not equals to BA. For all AB belongs to G. Therefore, G is not an abelian group with respect to matrix multiplication. Matrix multiplication. Okay. So this is an example of a non-abelian group. It forms a group, but abelian property is basically not holds. So obviously we can conclude example of a non-abelian group here. Now we come to the next question, question number 4. Prove that the set S is a group under matrix multiplication where S is the set of all 2 cross 2 matrices A, B, 0, C such that all A, B, C are real number and A, C are non-zero. Next question is it commutative? Justify. Okay. So we have to prove here this is a group, but then we will check it is commutative or not. So what is exactly given for the set S? How to solve? Come to the solution now. So what is here is S equals to all the matrices of the form such that ABC are real number and AC are basically non-zero. So first we will check it is closure or not. So closure property, let two elements say A1, B1, 0, C1 and B, A2, B2, 0, C2 both are belongs to S. Then what we can say? We can say A1, B1, C1, A2, B2, C2 all are real number along with A1, C1 non-zero, A2, C2 is also non-zero. So then if we multiply it AB, that means A1, B1, 0, C1, A2, B2, 0, C2, the simple matrix multiplication. It will be A1, A2, A1, B2 plus C2, B1, A1, B2 plus C2, B1, it will be 0, that will be C1, C2. And it obviously belongs to S because all A1, A2, A1, B2, C2, B1, C1, C2 all are real number and if we multiple A1, A2, C1, C2, that we can write A1, C1 into A2, C2, and that will be non-zero. So this is by step. So what we have shown here, AB belongs to S for all AB belongs to S. So closure property holds. Now we come to the next property. This is associative. Associative property. Associativity. So we'll check, let A, B, C all belongs to S, where A is basically A1, B1, 0, C1. B is A2, B2, 0, C2. C is A3, B3, 0, C3. Then obviously A1, C1 non-zero, A2, C2 non-zero, and A3, C3 are non-zero, and all AI, BI, CI real number for all I equals to 1, 2, 3. Since we know ABC equals to ABC for all ABC belongs to M to R, set up our 2 cross 2 real matrices, and here is S is subset of M to R. So by hereditary property, what we can say? We can say ABC equals to ABC for all ABC belongs to S. So associativity property holds in S. Now we come to existence of identity. Existence of identity. So we have here I2 belongs to S. I2 means where I2 is basically 1, 0, 0, 1. And A multiple I2 equals to I2, A equals to A for all A belongs to S. So that means I2 equals to 1, 0, 0, 1. The identity matrix of order 2 cross 2 is the identity in S. So existence of identity is also done. Now we come to the existence of inverse. Existence of inverse. How to check existence of inverse? So let A belongs to AB, 0, C belongs to S. Then obviously all ABC are real number and AC are non-zero according to the property of S. So since determinant of A, this is basically AC and this is non-zero, that implies A inverse exists. Because the determinant is non-zero. And what will be the A inverse? And A inverse will be 1 by determinant, that means 1 by AC, and that will be the principal diagonal element is interchange, and off diagonal element will be a minus sign, just to multiply it minus. Okay, that will be A inverse, and hence we can write A inverse. So A inverse, if we multiply it, so that will be 1 by A minus B by AC, 0 and 1 by C. And hence we can say A inverse belongs to S. Why? because all are real number. 1 by A, 1 by C, since AC non-zero, that implies A is non-zero and C is also non-zero, and that implies 1 by A non-zero, 1 by C non-zero, and that implies 1 by S is non-zero, and all 1 by A, 1 by C minus B by S all are real numbers. So A inverse belongs to S. So therefore, for all A belongs to S, there exists A inverse. This is also belongs to S, such that A inverse equals to A inverse A. This is basically the identity of S. So hence inverse is done. So thus we can conclude, thus S is a group with respect to matrix multiplication. Okay. Now we come to the commutative property again. So now we come to the second part. So just you take 1, 2, 0, 3 and 4, 5, 0, 6 belongs to S. Okay. So take, this is your A and this is your B. And then you will take AB 1, 2, 0, 3 and 4, 5, 0, 6. And you will multiple. So that will be 4, 4, next 5 plus 12, 17, next 0, next 18, and BA 4, 5, 0, 6, 1, 2, 0, 3. So this will be 4, 8 plus 15, 23, 0, 18. And here you just see that value is basically different. Here you will see 17, here 23. So therefore, AB not equals to B. And thus, S is not a commutative, because commutative property does not hold here. Commutative is a group but not commutative. So that means it is not a commutative. Thank you so much. That I will again explain more.